All right, it looks like we're at 5 after the hour. So thanks everyone for attending this tutorial. This is the RAPIDS, or Bringing Dask Workloads to GPUs with RAPIDS workshop, or rather tutorial, where Ben Zaitlen and Nick Becker, two NVIDIA employees, are going to walk through how to use RAPIDS with Dask. Ben is the head of the Dask RAPIDS team here, or I think anyone who's been involved in the community likely knows Ben or has interacted with him before. Nick Becker is on the workflow side, where he works really closely with customers and oftentimes giving tutorials like this to them to help them out. So I'm pass it off to those two, and look forward to everyone learning a bunch.
Thanks, Jake. Yeah, as Jake was saying, my name is Ben. I work at NVIDIA, wearing my RAPIDS shirt. But if I was at the conference, I'd maybe cut it in half and wear like a Dask shirt, or half a Dask shirt and half a RAPIDS shirt, because I wear two hats. So I'm going to give a quick overview for those of you that were in the GPU workshop just before. You've probably seen some of these slides. If not, this will be very informative. So I apologize if it's redundant to some folks. After this quick presentation, we'll go through a handful of notebooks. We're trying to come up with ways to get everybody access to GPUs. Didn't happen this one. I imagine that at the next summit, we'll be able to make that happen, that there'll be better tooling in place to make GPU data science available on demand. Yeah, so with that said, let's get into it. So over the years, data processing has changed quite a bit. Actually, this slide is only going back to probably like 2010, when Hadoop kind of takes over. And what you see at each stage, as you move from Hadoop to Spark to traditional and then to RAPIDS at the end, is that these little gray boxes are getting smaller. That within these same
Ben, sorry.
things.
Is it possible you're sharing a different slide deck?
Nope.
We see accelerated hardware return to the past.
Oh, yeah. Shoot. Yeah, that's the wrong one. I mean,
it's good look.
I thought
good looking slide, but yeah.
Yeah, I meant to just talk about that, but not. Yeah, why didn't this work? Desktop 2. There, is that working?
We've got an agenda now.
Tutorial agenda.
Okay, thanks, Nick. Yeah, so this is the slide that I was actually trying to reference. And these are the gray bars, these HDF reads are going away as you move from traditional Hadoop processing all the way down to RAPIDS. The slide that you just saw was just a mental reference for me to remind myself that traditional data processing is actually older than Hadoop, which is shocking. And how people get acceleration is older than GPUs. That in the 70s, if you wanted to go faster with the same code, or not the same code, if you wanted to go faster, you had to build a whole new computer. So we had analog computers, we had custom circuits, custom chips, and that was a really exciting time to be in because there's all this customization. It was everything was greenfield back then. But it was also a terrible time for somebody that actually wanted to do analysis, that just wanted to move on with the rest of their day, or trying to write down a statistical query and having to rewrite that because the hardware and the software changed underneath them. So we've learned a lot from the 60s and 70s, and where we're moving now is trying to get that next 10x by switching out the hardware and maintaining the same APIs. GPUs are a really good place for us to move to because we can get that acceleration, because it's general purpose, and because NVIDIA and RAPIDS have made the investment in maintaining the APIs in the PyData ecosystem. So explicitly what that means is we have these analogs between our traditional ecosystem that we all know, so NumPy, Pandas, scikit-learn, and things that RAPIDS and other groups have built. So from NumPy, we can go to cuPy, a GPU accelerated version of NumPy. From Pandas, we go to cuDF. And from scikit-learn, we can go to cuML. Scikit-learn is rather broad. So the parts of cuML that we're trying to attack or trying to accelerate are the modeling and classifiers, but we can still leverage parts of scikit-learn because we're meeting the APIs and objects of scikit-learn within cuML. So a cuML model looks and feels a lot like a scikit-learn model. It's just all processed on the GPU. So the RAPIDS ecosystem now looks like this, where we're trying not just to handle a given vertical. It's not just data preparation, but the entire workflow, the end-to-end workflow that most of us actually need to get done. So not just data preparation, not just fast model training, and not just visualization. And what underlies all of those things is these key libraries, cuDF, cuML. We also have other libraries like cuGraph. Obviously, people here should be familiar with Dask, PyTorch, and we've also accelerated visualization libraries like Plotly, or PyVis, or cuXFilter. The reason that we can do all this is also because not just that we're meeting these APIs, but because we're adopting other lower level libraries that meet a spec are spreading throughout the ecosystem. This is mostly Apache Arrow that I'm referring to here. So because we've adopted Apache Arrow, not rewritten our own memory layout, we can leverage and move back and forth between a lot of libraries and intermix within all of these libraries within Rapids as well. But the ecosystem isn't just CuPy, cuDF, and cuML, it's actually expanding. I mentioned cuGraph on the previous slide. More recently, we released cuSim, which is scikit-image GPU accelerated library, or cuSignal, which is SciPy Signal. So we're continuing to kind of push into this world that we can get not just 10x or 20x, but maybe 100x. Those are the goals that we have in mind. And we're seeing really good adoption of this generally. People are finding not just that this is marketing material, or they're not just believing our benchmarking releases, but that they're going out and using these tools and getting the results that we claim that you can get. We continue to expect this to grow. So for today, we're going to mostly focus on these three highlighted libraries, cuDF, cuML, and Dask. So cuDF is the underpinning of more or less all of the Rapids ecosystem for doing tabular data. It has a familiar pandas-like API. It's extremely performant, and it uses a lot of standard tooling within the C++ and GPU ecosystem. So a lot of the libraries within Rapids kind of follow this model with Python on top, Cython to connect us to an underlying C++ library where all the CUDA bits are. And then within CUDA, things like Thrust, Cub, and Jitify. If you're unfamiliar with those things, that's okay. The main takeaway from this is that cuDF looks like pandas and it's extremely fast. This is where we show you how fast it is. So on a single GPU, we can get these kinds of speedups when we do a particular algorithm, in this case, a merge, a sort, and a group by. And that's pretty compelling, I think, that we should keep on exploring. Is it just a merge, or is it just a sort and group by? That's not all that there is to workflow. We also have significant string support. Turns out that we tend to think of, or before joining NVIDIA, and I think a lot of people out there think of GPUs as being really good at matrix algebra, or sorry, linear algebra or matrix math. And we have a preconceived idea that I would be really bad at strings. And it turns out it's not the wheelhouse of GPUs, but it's still really good. We can keep on pushing in this area. So a major part of data science is not just time series analysis. At probably every institution, there will be some text manipulation that's required. And it's also not just lower find and slice, but more complicated things like NLP, traditional NLP things like tokenizers and things like that. On the ML side, we see the same thing that we saw in cuDF, that we have this Python layer, Zaitlen to connect to an underlying C++ library. And then all of that actually is exposing things that CUDA, that NVIDIA and CUDA have already built. So things like cuBLOS, cuSparse, cuSolver for the primitives that traditional ML algorithms need. And similarly to cuDF, we can also show how we're performing on these particular algorithms over a CPU. So k-means, lasso, linear regression, PCA, random forest. Again, not deep learning, but traditional, it seems weird, but traditional machine learning. And we have 26, I think, GPU accelerated algorithms already supported. We can keep on growing and keep on going after more performance. Yeah. This is actually a little bit of an older slide. This is a couple releases. So I imagine that we should be going a bit faster with the A100s that were recently released. And as I said before, it's not just a fast group by or a fast XGBoost in this case, but we need to look at how a workflow is accelerated end to end. There's lots of things to be considered when we start doing a full workflow, how data is piped in to the device, whether there's too much data and we need to spill, then how that data is chunked up and loaded into XGBoost or into a particular ETL. And you can see that not only are things a lot faster at the very end, but that they're significantly faster and we're getting faster over time as well. If, however, all you needed was just I/O, we can solve that for you. If you just needed XGBoost, just GPU XGBoost, we can also solve that for you. But really, I think I'm beating a dead horse, but putting all these things together, we get that acceleration that we're looking for. And with that acceleration comes not just, I mean, the obvious thing to say is that, great, so this ran a lot faster. What do we do with that extra time? The human part of this is that it allows us to explore a lot more ideas, that we can run more simulations, we can run more experiments. And in the case of this particular example, it allows us to be in a different mindset when we're at the keyboard, that if we can move from 3 minutes to 10 seconds, that's a very different kind of experience than when you go from 3 minutes to 1.5, right? We're in less than the amount of time that it takes to make a cup of coffee. We're in the time range that it takes us to go back to Twitter or be distracted by something else. We can keep on iterating a lot faster. So we can take this traditional PyData ecosystem and scale it up with Rapids, and you can also scale it out with Rapids. The scaling out bits we can do, we're at the Dask Summit, so we're mostly going to be focused on Dask. There are other groups that are represented here as well. Actually, Blazing SQL gave a talk earlier. So we can scale things with a SQL engine, and we can also scale with, there are also hooks into Spark as well. Because we're at the Dask Summit, or not just because we're at the Dask Summit, but I work on the Dask team, I work within Rapids. We spent a lot of time thinking about how to improve and how to deploy GPU data science. Because Dask already has hooks into things like Kubernetes and Yarn, the community has thought a lot about deployment. It's thought a lot about being, Dask itself is already trying to meet the APIs of NumPy and Pandas and scikit-learn. It was challenging, but it made sense to also slip Rapids and cuDF and cuML into that world as well. So because Dask can do these things, Rapids and cuDF can do these things as well. It also became very easy to identify what communities we could try to accelerate. And when we started getting our hooks into this world of GPU data science, we realized that PyData folks want a lot of dashboards. We want a warm, fuzzy feeling, especially for something as unfamiliar as another device. So people within the Rapids team they took Bokeh and the ideas from the Dask Lab extension, and they hooked into NVML to show us what's happening on the GPU. I'll demonstrate how to get this up and running later in the talk. But what you see here is a Jupyter Lab setup with an extension called NV Dashboard, where we start up a Dask cluster that has 8 workers, each worker pinned to a GPU. We read in some data and then we persist it. And what you see on the right is us in real time seeing what's happening on the GPU with the utilization. We can also look at the memory consumption, PCI throughput. There's other things, there's other bits that we can get into later. But this world we're trying to make as friendly and inviting as possible, and also give people feedback that things are actually happening on this device. It turns out that many people within NVIDIA and many of the customers that NVIDIA also has really like this extension. They don't use this all the time for Dask. They're using this for their other the other libraries that they build because they want a real-time information feedback loop of what's happening on the device and whether things are running correctly or incorrectly, whatever that means. As I said before, we saw downloads of who's using it. We actually have a ton of contributors, not just cuDF is really trying to go after an ecosystem model where we invite a lot of partners and other people to contribute. We have a lot of early adopters. Walmart gave a talk earlier about their successes with Rapids. And we are fully open source. So if you have, if you are a tool builder, please come join us. If you are a user, I encourage you to come test it out. We can deploy. We've worked also pretty hard at trying to deploy everywhere on all major clouds. You can also deploy with Saturn Cloud and Coiled, but we have customers at each of the major clouds and also at Baidu and Alibaba. I guess you can all refer back to this link if you download the slides, but there's lots of ways to get involved or to learn more. There's docs at rapids.ai. We have a Slack group. You can get started on Google Colab if you want to play with these things. I'm also happy, many of us are in the Dask Slack workspace and we'd be happy to engage with you there as well. So please come join us and come play. With that, I think we should get started. Are there any questions before I move on? Okay. I'm going to take that as a no. So I'm going to run through the first notebook and then hand it off to Nick. So this is our standard intro to cuDF notebook. This is a Jupyter Lab session that's running on a machine underneath my desk. It has 2 GPUs. Here's this NV Dashboard plugin that we can look at our GPU memory. We maybe want that. So I'm going to just drag that over here. Maybe we also want to look at utilization. This is what's going to tell me, this is what's going to inform me what's happening on this box. So this notebook is modeled after the 10 Minutes to Pandas notebook. So we're going to bring in some, get a kernel. This is the Rapids 19 kernel. Actually, maybe I should just quickly show. So this is the Rapids AI page. We can get started. Here's some like requirement information that is particularly useful. And getting started is just kind of installing all these things for a variety of selectors, different versions of Linux, different versions of CentOS, different versions of Python. I think 3.9 is maybe will happen in a few months. Different versions of CUDA as well. So I had run this previously, so we'll just bring in some imports. we'll do some standard pandas-y things. My goal, or our goal with this is, this should be a pretty boring section for everybody. The reason that it's going to be boring is because I'm just going to show you how the cuDF API maps to the pandas API, and not just in very simple ways and more complicated and more complex things that we can do in pandas that you should expect to do in cuDF. So when I do something like this, where I have an empty data frame, fill in some values, and then I aggregate those values, I call sum, I should be able to do the same thing and get the same values out. But all of this is going to happen on the GPU. So we see a little bit of memory that's being used here because this is running on a machine that is running X Windows. But if I import this, I see a little bit of utilization stuff. And then now I'm taking up a little bit of memory. This is GPU 0. So I have probably around 300 megabytes for the CUDA context. And then however much data is here, maybe like a meg or two. So we're, again, just the same things that we expect from pandas. We create an empty cuDF data frame. We fill in a particular column. We also create a column of floats. And then the printout is the same. Let's do this. So if we look at our D types, we also have an int and a float, except again, all of this is happening device side. Can also call sum on that particular, on the value column, and we get a float out. Again, we should see our utilization just tick a little bit when I do that. Maybe not, maybe that happens. I think it's sampling maybe faster than it takes to run the sum. So just like in pandas, how they have series and data frames, cuDF also has series and data frames. Can handle null things, which is really nice. At the beginning of these experiments, null support was not there. Can do things like creating a data frame just as you would, again, with pandas. Sorry, it's like important, I think, for participants to understand that everything is happening device side, and I will keep on saying that. But I'm also apologizing that this is going to be, this section is a little bit dry because it's like it's super exciting for me because all like this, there's so much work that goes into making this happen. But for the user, they shouldn't see any, there should be no difference between running cuDF and running pandas. That's like the takeaway from almost every single one of these cells. So again, we're gonna build a data frame of dictionaries. We'll convert from pandas this time. And then now we have a cuDF data frame. So not only can we build objects directly from, not only can we build cuDF data frames directly from Python objects, we can also build them directly from pandas. So converting, moving from, you might hear these terms of moving from host to device or device to host. That's saying, I have something that's running in pandas or running in Python, that's running on CPU memory. How do I move it to the GPU? These are these functions where I create a Python object, in this case, a dictionary, and I load it onto the GPU with this data frame call. Same thing with this one. I'm building a pandas data frame that exists on the host, and I load it from pandas onto the GPU.
Ben, would you be able to zoom in a little bit into the notebook so the font could be slightly larger?
Yeah. Is that better? Nick, do you think that's better?
I actually didn't see a change, but it might just be my screen.
Okay. Can I call on somebody else to confirm that something's been changed? Because I want to make sure that folks can see this. I think I saw Julia here earlier.
It looks good. It's
Okay,
good, Ben.
great.
Yeah, that's good.
Thanks. Some things we've pulled in from the Dask ecosystem, like being able to quickly generate data sets, is really convenient. So we also have this nice cuDF dataset time series function that we can very just quickly have a data frame that we can start playing with and do things with. In this case, this will build us some random IDs, some random names, and some random floats between -1 and 1. And just like with pandas, we can get the head, we can sort this by some values. Sorry, this is referring to an earlier data frame, to DF. And we can also select in the ways that we should be able to. We can select a single column with the accessor. We can also use df.a, as it's demonstrated here. Sorry. We can also get the location. We can randomly index into all these places. So these are these things that when libraries try to build equivalents, at least in the past, they're not trying to handle all of these different interfaces. And these are important to do because when you go to an individual or a group or an enterprise, and you say, here's this drop-in replacement for this tool. But you have to like change actually the API. So we only support these particular kinds of interfaces. Then that becomes just that little bit of a block for people to adopt it. And the Rapids group has gone through great pains to make sure that all the different pandas selections are possible. This is also a pain for Dask as well to make sure that different kinds of selections are supported. So we can get like the first iLook values. We can also get a slice of them. We can also directly index into them. Again, not terribly exciting, but I think motivating in how far Rapids is trying to push in terms of usability and ergonomics for the average user. So I think I've already done all these. I did this ahead of time like a good student. So all these solutions are solved. So we can select rows 4 through 9. It's already done for us. We can also select out a particular set of values. So getting just the values that are larger than 15. Again, things that are available in pandas. We can also use the query method, which is a really nice API for asking what values match b equals 3. Or we can use this. I've actually never used this particular kind of query method. I find it odd, but other people use it. Yeah, or same thing with this comparator operator. All of these are, the logical operators are supported. Sorry, I'm gonna move through this a little bit quicker so we can get to cuML, which is a lot more exciting. We can also query things that are a little bit more complicated. We can handle missing data. So if you recall what S is, there's a NaN value here. Actually, this is pretty interesting. So within cuDF, there's an NA, a general NA object. And that's because a NaN is listed as a float, I believe, within the pandas world. And we don't want to cast every column we want null support, not just for integers and floats, but also for date time objects and for strings. So cuDF built this null object, which can be mapped into these other. We can handle this generally throughout the Rapids, throughout cuDF. But in any case, you shouldn't have to care about that. But we can run these standard. We can handle still fill-no operations. There's a lot of, all the statistics are supported. So mean, var, kurtosis, standard deviation. Also, interestingly, this took a little bit of time to get up and running the describe method, which is useful. I use this actually a lot. I imagine all of you do as well who do data frame things. This is where things start to get a little bit more interesting for folks of how do you handle UDS? Not the entire data frame world is not just sums and means and aggregations, but applying a UDF to a function. So in this case, I can take this function num plus 10 and apply it to this series. What's really cool is that this doesn't if you knew a little bit, but not everything, you might say, oh, well, doesn't that cause a device to host transfer because this is a Python function and we're applying it to something that lives in the GPU. You might assume that we have to bring the data down from the GPU onto the host, run this function, and then push it back to the GPU. That's not the case. That's because we can leverage awesome tools like Numba that can take this function, compile it for the GPU, and then run it there. We talked a little bit about strings in the slides. So we will have, again, this none becomes this NA value. We can call lower on it, we can call upper, upper, we can call splits. We can concat data frames and we can append data frames. And then this is where things start to get a little bit more interesting, where we build two objects and then call merge on it, do an inner merge. This is actually where cuDF's wheelhouse really is doing joins and merges and group by aggregations is where cuDF really starts to excel, and you see huge performance gains. Here's a split apply combine example where we're going to build a data frame that has columns A, B, and C and add column 1 and 2. We'll group by add column 1 and sum. We're going to build up to a more interesting example in a second. We can do the same thing and run, again, there's within pandas, there's multiple aggregation interfaces. And this is actually where things are also a little bit different on a GPU, that we can actually run these aggregations in parallel on the GPU. On the pandas side, this is running max and then mean and then sum. And this came up recently in trying to think about the differences between Dask and Dask cuDF, is we can build a slightly different route in Dask cuDF, which we'll get to in a little bit, when we run multiple aggregations on a group by, because we can take advantage of that parallelism that's inherent on the GPU, that's not inherent on CPUs. Yeah, I'm going to just skip over this and get to a more interesting time series example. So we'll build up time series dates. We can query these dates just like we do in pandas. Can look at, these are, again, these nice interfaces that we expect to be able, that when cuDF has a datetime object, we expect to be able to convert to .date or day or hour or month. And we can do those kinds of operations. So you can see down here. So we can assign in this, we're getting the day of that particular time series. Again, we want this experience to be as transferable as possible. When these things don't exist, I think that the Rapids community has also been particularly responsive, saying, oh yeah, we should make that available to users. So many of the customers and people that use Rapids, or people that use Dask, or people that use pandas for that matter, will do a lot of data frame manipulations and then want to do something later on with that data. So they might have, like, the canonical workflow in this is some ETL thing, then give me back all the NumPy values, and I'm going to do some ML thing, and then I'm going to write that out to disk or do some visualization. So just like with pandas, we can call values. And in this case, values isn't going to return a NumPy array, but a cuPy array. And this is a good example of where cuDF meets the rest of the ecosystem. That cuPy can be moved, cuPy arrays and cuDF data frames can be moved back and forth with zero copy and zero transfer. That's because of things like the CUDA array interface. I'm not going to go into that here, but if you're curious, I would search for CUDA array interface at NumPy, and leveraging these community standards lets us do these kinds of these operations of moving between different libraries within the GPU data ecosystem. A common problem that users have is I have this GPU thing, I've done my thing, I've done something with it. How do I bring it back to pandas? How do I bring it back from the host? So we can call the toPandas method. And we can also convert to take a data frame and convert it to a NumPy, to an ND array. You can also convert particular series. So now we're going to get into something a little bit more interesting, where we're going to create a CSV file and then read it in. So because cuDF has fast string processing, we can do things like read in a CSV. You can also read in Parquet files and org files, but CSV is usually where people start out, where data hopefully doesn't live long-term, but maybe starts off as a CSV file. Similarly, we can also take our data frame and now convert the previous CSV data and make it a Parquet data set, just like you can with pandas. Okay. I think this will be a little bit more interesting now. We'll see some fun stuff. Here we're building a very large pandas data frame, 10 million random values. We're going to sum it. That took a little bit of time. And then when we do it with cuDF, it will take just a little bit of time. Yeah. So that's a huge improvement. Going from milliseconds to microseconds is significant. Going from minutes to seconds is significant as well. Hopefully, I'm going to run this again. You can see that our GPU utilization is doing some fun things on the right. For a more realistic example, we'll build something that looks a little bit like sensor data. So this could be something that the climate science world is familiar with. You might use tools like pandas initially, maybe you'd move on to X-ray. For now, we'll just stay in pandas land. Here we're building a time series with some random values and associated hours, minutes. This is just construction of the data. So this took 17 seconds. When we do this group by operation and look at the max of value, it takes 3 seconds, which is not wonderful. And if we time the construction of the data, it's a second, and doing this group by mean, it's 40 milliseconds. Again, significant performance benefits when you do these GPU operations. Yeah, exercise 7 is where we would traditionally spend a little bit of time playing with time-int and time. I think in the interest of moving on, I think I'll hand it over to Nick for cuML. Before I do that, are there any questions about this? I'm sorry if I bored you to tears. This is really, the Rapids team has worked so hard at getting these APIs working and making sure that things run performant, that it's hard to make a motivating example here, but I hope that I've convinced you that this is worth a look at. Okay, if not, I'll turn it over to Nick to go into cuML.
Thanks, Ben. As mentioned at the beginning, my name is Nick Becker. I am an engineer on the Rapids team and have been working across the whole ecosystem of libraries on development and applications. And this is going to be the first of several notebooks that we use Dask for. After this notebook, Ben will take over again and give an overview of how to actually use Dask and Rapids together. This was going to give a little teaser of that. But to start, it's going to introduce our machine learning library, cuML. I'm going to share my screen. If you can't see this in a moment, someone please be loud, and I will try to resolve that. But hopefully, you'll be able to see this in a second. So I'm going to assume folks can see this. You should see a Jupyter Lab setup where I have 3 notebook tabs open, one of which is titled Intro to cuML. And if folks would like me to zoom in, please just let me know. The sort of high-level overview of cuML is that it is a GPU accelerated machine learning library that feels like scikit-learn. So there's some key principles that we use when developing this library. One of which, as expected, is to match the scikit-learn API wherever we can. It doesn't mean it's always possible, but in general, cuML estimators and preprocessors and everything associated should feel and act like scikit-learn estimators. The second principle is that we want to accept flexible types, but return predictable types. So we want to accept NumPy arrays, cuDF data frames, cuPy arrays, PyTorch tensors, any kind of standard-based Python object. But when we accept flexible types, we want to return the same type we received as input. So if I pass in a GPU data frame, I should expect to get back a GPU data frame. If I pass in a NumPy array, though the actual processing will happen on the GPU, I should expect to receive back a NumPy array because that's what I gave it. That sort of leads into that third principle, which is we're using GPUs. The reason we're choosing to use an accelerator for our generic processing is that it's fast. And so the third core principle of cuML is to be fast. And we'll go over a few examples here that give you a clear sense of how cuML works and a very quick example of the serious performance benefits you can gain. So to start, this notebook should look very familiar to folks familiar with scikit-learn. I'm not importing scikit-learn, but the namespaces I'm importing should look identical. So I'm importing from the cuML model selection namespace train test split, which lets me split data sets into a train and a test combination. I'm importing make classification and make regression to create random data sets. So in this case, I'm going to create random classification and regression data sets. They're going to be 100,000 rows by 20 columns. This is, of course, arbitrary, but I'm going to create these. And we're going to now walk through cuML's regressors, but only a subset. Of course, there isn't time for all of them, and the classifiers and clustering and things like that. Ben already showed on the right of the screen this wonderful dashboard we can see, so I won't go into depth about it, but you will see this light up. On this machine, I'm at the moment using one GPU. So as a result, we only see memory allocated on GPU 0. So with that, we can start looking at cuML. We can do things like run lasso regression. And we can see that, of course, 100,000 rows on a GPU, this is essentially instantaneous as expected. It gets some performance. But we can see that it's the same experience as scikit-learn. We instantiate the model. I'm calling it CLF for classifier. We call the fit method and pass in our data. Now, these are GPU arrays, they're cuPy arrays, but they could have easily been NumPy arrays. So it fits the estimator. Once fit, we could call predict, but instead we call score, which, like in scikit-learn, for a regression model, by default is going to represent the R² value on the test set in this case, because I'm passing the test data sets. And like scikit-learn again, we can access the coefficients themselves from estimators that actually have coefficients. We can also do ridge regression. Ridge regression is another type of generalized linear model. As expected, they perform somewhat similarly, as this is a pseudo-random example. But we can also do non-parametric modeling, things like k-nearest neighbors. In this case, we can do k-nearest neighbors regression. On this data, it happened to be the case that this R² value is noticeably lower. Like scikit-learn, we expose a variety of different parameters that we can use, including changing the number of neighbors, changing the distance metric, and many other things. By default, we use 5, but we could have easily used 10. In this case, that happens to be a little better at generalizing to the test set, which suggests that 5 may have been overfitting. The parameters we use are documented in the cuDF API documentation. But if you're in a notebook, you can always make a new cell and hit the question mark afterward to look at the signature for the function. And the doc string will tell you all of the different things. In this case, you can choose weights, you can choose metrics, and everything that you'd expect. So for classifiers, we also support a broad array. One of them is logistic regression. Again, these will essentially be instantaneous because on a GPU, you can process hundreds of thousands of rows so quickly. But conceptually, this could scale to millions, and it does clearly scale to millions, and we'll see that in a moment. But we can also do things like changing the penalty in our logistic regression model. We can use L1 regularized logistic regression. We can do L2 regularized. We can do elastic net. All of these kinds of canonical solvers we can do with our logistic regression model. And we can also do that same k-neighbors estimator as a classifier. And like before, we can vary the number of neighbors. In this case, it's quite clear that this is performing significantly better than the cuML model for logistic regression. That's the nature of this problem. The separation of this data happens to be better suited to this non-parametric model. And we can change the neighbors again. And it turns out, again, we do better. It sounds like 5 probably is not a good default for this arbitrary data set. And that sort of leads us to the next point, which is kind of why you would want to do this. It's great to train one model faster. In fact, it can be critical. If the model takes 30 minutes today on a CPU, you can maybe do it in 1 minute on a GPU. That's wonderful. But if you're doing things like hyperparameter optimization, where you train multiple models, or cross-validation, where you want to verify performance in a way that isn't sensitive to splits, suddenly you're training more models, and those speedups start to really matter in time, but also in cost. And to just drive that point home quickly, we'll import k-nearest neighbors and put the data on the CPU. With CuPy, you can call the get method to just put the data into a NumPy array. So we'll run this right now. So this is running the scikit-learn standard k-nearest neighbors. It is using every core on this machine. In this particular machine that I'm running on, there are 40 physical cores, so there's 80 virtual cores. And so this is a pretty beefy machine. It has beefy GPUs as well as beefy CPUs. So this is going to take quite a bit of time. In fact, it's actually going to take about a minute. So I want to actually kind of like let this sink in. If we were to do this for one iteration, it'll take about a minute. But we already saw that 10 nearest neighbors in terms of making a decision for classification was better than 5 in this data. But again, that's an arbitrary choice I made. What about 12? What about 15? When you start doing things like random search, grid search, Bayesian optimization, all of these kinds of strategies, this becomes untenable, especially if you're running in the cloud, particularly if you're running in the cloud, where your costs are essentially just marginal on the time. Every time you save minutes, you save dollars. And so this, in a second, is going to finish, and we'll run the same code with cuML. Notice that it's literally the same API. I'm not going to run n jobs because we're not using multiple CPU cores. We're using the GPU. But it's the same instantiation, the same fit, and the same score. And while this is going to take about maybe 60, or perhaps it's even taking 90 seconds in this example. So it took about 90 seconds in this example. In the GPU version, it's essentially instantaneous. And you can see that this is non-parametric. It clearly is getting the same solution. It's just the scikit-learn once is doing some rounding. You can go from things that take a minute on 100,000 records to things that take 175 milliseconds. And if you're doing 1,000 of these, suddenly you can go from hours to just minutes, and it's really exciting. So going back to cuML, it's pretty clear that it's very fast, and we want to see how we can, fill out that world of not just the classifiers we've seen, but a few others. There's also support vector machines for classification and regression. There's also clustering. You can do clustering with things like k-means. There's also many other clusterers, and they all return exactly what you'd expect. You can get the cluster centers. You can do things like density-based clustering with dbScan. There's work in progress for all sorts of things as well. And I encourage everyone to look at the API documentation for details. Again, clustering is not the whole story. Sometimes you need to do dimensionality reduction. We support standard dimensionality reduction techniques like PCA, there's UMAP, there's TSNE, all of these canonical approaches to doing these problems run on the GPU and are GPU accelerated as a result. But beyond that, there's also pre-processing, which is surprisingly time consuming at scale, it turns out. Doing things like discretizing variables into, from continuous to categories is a common feature engineering task, or creating binary variables or things like that. These things take time at scale, but on the GPU, with the massive parallelism, we can do them essentially instantly. Another feature that's very, very useful for doing hyperparameter optimization is feature interactions. If you have 20 features in our example, you might want to explicitly test feature interactions. It's very common in statistical-based modeling for actual causal inference and looking at things like that. But it also is common for hyperparameter-based pure optimization, trying to find the best solution. And so things like polynomial features, to go from 20 raw features to all of the interactions giving us hundreds of features, can be done essentially instantly. And the result of that is, though, now that you have hundreds of features, your model is going to slow to a crawl even further. But on the GPU, it doesn't happen, which is really exciting. There's also, of course, NLP processing, which we'll see in a moment, where you can do things like stemming. Porter stemmer is just one of several commonly used algorithms for stemming words into their roots. So in this case, revival, the root of that word is revive. Singing is sing, and so on and so forth. And sort of just before we start talking about Dask, we've done a lot of different things. We've tested preprocessors, we've tested estimators, we've seen that they're much faster than the CPU equivalent, even on 80 CPU cores. We can also put it all together. We can do a pipeline. Pipelines are a wonderful scikit-learn API that cuML exposes. We are incredibly grateful for so many reasons, really, to the scikit-learn team, but in particular as well in this moment, grateful for the pipeline API, which we wrap into a friendly namespace, but it's really the scikit-learn code that we're just grateful to use. So you can see that some support vector model can get 97% accuracy in the classification task. But if we make a pipeline, we might try scaling our data. cuML supports scaling our data. And if we do that, we can actually see that it's a different result. In this particular case, with this random distribution of data, it actually didn't even help. But we might have wanted to test that, because it turns out if we do another pipeline, we can see with polynomial features and scaling and the same model, we can actually pretty materially increase our data if this is an important problem. Increase our results if this is an important problem. We increased accuracy by 0.5% by adding this pipeline. That's very significant depending on the problem. And so cuML lets you do that just like you can do on the CPU. Another key area that cuML allows you to kind of have that seamless experience is with tools like SHAP for explainability. You can do things like use the kernel explainer you would use with SHAP in cuML, and you can arbitrarily get SHAP values for something like a support vector machine. You, of course, can do this the way you'd usually do it, and you might do this with XGBoost or a forest model. And if it's an XGBoost, it's, of course, baked in. You can just use it natively supported on the GPU. But you can do this with arbitrary models as well, which is really exciting. This SHAP in particular gets really computationally expensive when you start doing feature interactions, and the GPU starts to provide multi-hundred-fold speedups. Of course, we don't just want to train our models and be done. We likely want to train them for a reason. Sometimes that means we have to deploy them elsewhere. So we can do things like pickling our models. We can store them and persist them and bring them up by reconstructing them somewhere else. In this case, we can show we can literally use pickle to just take our k-means model, in this case right here, and we can dump it to the file system. We can load it back up, and we can see that, like before, we have our labels. We can actually do more. We can even pickle the whole pipeline that we made. That pipeline, we can pickle the whole thing, load it back in. Actually, I think you might have just seen on the bottom right, the GPU utilization just flashed up because this was enough computing power to register. And again, we can fully recreate that entire pipeline, which is really exciting. So again, this has been great. With 100,000 rows, all of these things were essentially so fast, it didn't even matter. But when you start talking about tens of millions or hundreds of millions of rows, or you start talking about massive scale hyperparameter optimization, you want to be able to scale out to multiple GPUs. And this is where Dask shines. We can create a GPU cluster with 2 lines of code. And I'm going to do that right now. We can import from Dask distributed the client. This is the same as you'd normally do. And Ben will go into some details on this in a moment. But with this import, instead of importing local cluster from Dask distributed, we import the local CUDA cluster from Dask CUDA. I'm arbitrarily picking 2 GPUs. This machine happens to have more than 2, so I'm just limiting it to be respectful of other people who might be using this or might need those resources. And so with 2 GPUs, you can see that I have my Dask dashboard. This is the same as it always is, and Ben will go into detail, so I won't focus on it. But essentially, I can do things like run distributed clustering. In this case, I'm going to create some distributed data with the make blobs API, which is a scikit-learn API that exists in cuML. And as a result, we've implemented it for cuML Dask. I'm going to make some blobs, in this case, just very small data set, just to show that we can do it. And I'm going to run distributed k-means. And if we go to this dashboard, we'll see that we did a very small amount of work. And much of this work is actually just this sort of gray bar, which is deserialization. But essentially, we did it. It's running on 2 GPUs. Dask manages that for us. And we can then save that model. We provide a get combined model API for our Dask cuML models, which we can then use to get the single GPU model. We can pickle it, and then we're done. And we've got our cluster centers. We, of course, could have done this in the Dask world, but then maybe we couldn't have deployed it somewhere else. If we wanted to deploy it somewhere else, we can just recreate this same model with Dask and just use it for online clustering. So hopefully this introduction has given you a sense of a couple of things. Hopefully it's given you a sense of how easy it is to use cuML if you've already used scikit-learn. Hopefully it's also made it very clear that the time it takes to do something like k nearest neighbors in scikit-learn, even with 80 CPUs, just fades in comparison to the time it takes to do one iteration on the GPU. And hopefully you've also seen that we can scale this nicely with Dask. This has just been a taste. We don't have time to go into too much depth, but this is one of many machine learning models that can be scaled to multi-GPU and multi-node for the largest problems. So with that, I'll turn it back over to Ben. If there are any questions on this, happy to answer them now, or we can discuss in the chat.
Thanks, Nick. I posted in the Slack channel where you can get the slides and the notebooks. Sorry, I didn't see the questions earlier. My chat wasn't open. Okay. Desktop 2. All right. Okay, folks should be able to see my notebook again. Sorry for the back and forth. We're only going to do one more transition. So now we're going to get into Dask cuDF. So we have this, our layout looks, it's running on Jupyter Lab. We talked about this, just briefly about this NV dashboard extension. You can get that on GitHub right here. I'm going to move on to also talking about the lab extension, which you can also get on GitHub. I'm sure there's a talk, I think tomorrow, about the Jupyter Lab dashboarding that's available inside of Dask. So I'm going to kill this notebook. You can see that my memory went away, and now we're going to bring up this other notebook, intro to Dask, and let's close this. So I saw a few questions that we're already going to start touching on. So I'm glad that people are already thinking about problems that might come up. Within the Dask ecosystem, we built a specialized kind of worker. So traditionally, when you start up workers within Dask, you can specify the number of threads or the number of processes. You can have multiple workers that spin up that are attached to that fork multiple processes and multiple threads. For CUDA, because things need to be handled, because CUDA needs to handle things a little differently, or they're different enough that we couldn't force, or we couldn't push all these things into the traditional Dask worker. And instead, we've built a Dask CUDA worker. And just like how you can create a local cluster, you can similarly create a local CUDA cluster. I'm going to assume that my font is also small and just make it bigger for a second. So this talk will be fun, but also I hope to be kind of boring because it should just look like regular Dask. There'll be a few points where we'll say, oh, how do you handle these kinds of things? Somebody asked about spilling. So we can spill. We have to think about memory a little bit differently in GPU land, and that's because GPUs are resource constrained. As much as I want NVIDIA to make a 1 terabyte GPU, they haven't yet. But since I've been here, GPUs have gone from 16 gigabytes to 32 gigabytes to 40 gigabytes. They're getting bigger, which is great for us. They're also getting way more accessible. So I have 2 GPUs on my box right here. I think that's probably because I work for NVIDIA. But we're also finding that it's very easy to get multi-GPU instances on all the cloud providers because of deep learning, but also because of people wanting tools like Rapids easily accessible and available. So I'm going to start a Dask cluster or Dask CUDA cluster. So we'll use this tool called Dask CUDA to bring in local CUDA cluster. Here I'm going to bring 2 devices, 0 and 1. I'm also going to pretend that just like how we can force Dask to spill at a given memory limit, we can force Dask to also spill at a device memory limit. And this will be more motivating when we go to handling out of core, or in this case, out of device workloads. We've also told we've also told the GPUs to pre-allocate 16 gigabytes of data on every GPU. These GPUs, I believe, have 48 gigabytes of memory each. So normally you'd say, okay, it's just running here. We'd probably come over here. We'd spin up the dashboard. This is just a plug for how great the lab extension is. So you'd have to pull this down. You may have seen lots of us in the past do these sorts of things where we have a layout on our screen that looks like this. We're running some Dask operations. Let me close these. Running some like code on the left side, and we have the dashboard on the right. And that is fine. That's like fine, but it's not great. It's actually, I think it's kind of terrible, especially because people have already built this Jupyter Lab extensions to make this an all-in-one IDE. So we can do all the things that we can do on the dashboard. We can see right here. So we can have this task stream. I can pull this to the right. I'm gonna also maybe keep track of my GPU memory. The nice thing about the Dask dashboard hooks into GPU land is that it will be distributed. So every worker is going to report back what the memory is or what the utilization is. So I can see how things are running, not just on my local machine, but as I run on many machines. As a plug for later on, NVIDIA, when we do scale testing, we are going after 10 terabyte workloads on like 80 GPUs total across, I don't know, like 10 machines. I guess in the past, we've gone to like 128 GPUs, and people want to go even further. You want to be able, you not just want, but you need to be able to collect this kind of, you need this kind of instrumentation to tell you what's happening in your workload, because it's not going to go smoothly the first time. This is true not just of GPUs, but also of any distributed computing. It's really hard, it turns out. Sorry, so I have things kind of organized in the way that I like. Maybe I also want to keep track of how much actual memory I'm using. And maybe I also want to like look at the particular, maybe I want that over here. And I want to see which particular tasks are being processed. little bit smaller. Great, so now I've got things set up the way that I normally have them defined. So because cuDF meets the API of pandas, we can more or less use them within Dask with minimal. Well, I should say that there were significant changes within Dask to handle this other thing, but there weren't as many as there could have been because cuDF is going after the pandas API, that becomes the defined or the definition of what data frame objects look like, in the way that NumPy defines the API for what array objects look like. Sorry, so without further ado, let me get started. So I can create a Dask time series, and then we have some nice convenient functions to bring them into Dask cuDF. I didn't have to do it that way. All that this is actually doing is calling map partitions. So we could have done something that's like, if I had a Dask data frame, I could call map partitions. And then we saw before there was cuDF from pandas. So if you have, let's see. So if you have a CPU data frame that's a distributed Dask data frame, you can always move it to the device by calling cuDF from pandas. And that's more or less what this function down here is doing. It's just a convenience function because people wanted to maybe think a little bit, get into the headspace of Dask cuDF rather than Dask generally. Again, it's 6.5, half a dozen there for me. And we can do the same things that we just saw before. Again, this is like the boring parts. But now we have more visuals. So we can see all these things that are happening, but it's happening on the GPU, which is nice. We still have the same interactions that we expect from pandas do a thing, transfer some data, and here's our group by aggregation tasks. Let's keep on going. We can take that data and persist. So if you can see, and it's a little bit hard, but we've now like persisted a little bit of data. It's gotten, this one has maybe increased just a little bit. Actually, no, that shouldn't have happened. We're still in the, I don't know why there's a difference there. That's because, again, we pre-allocated 16 gigabytes of memory on the GPU. If people have questions about that, I'm happy to go into it. Maybe I'll save that for the end. I can't actually see the chat on this. So if there are questions, somebody should shout them out. So now with our data persisted onto both devices, actually, you know what, let's just pause just for a second. I'm gonna restart this notebook. And instead of, we'll just do just to show you how the things are actually getting loaded, I'll just restart the cluster without these two constraints. Everything should just come back up. And now when we do some GPU memory, we can see these things moving just a little bit, not a whole lot. That's all that I really wanted to show. Yeah, those things are really useful for me. It's useful for, I believe, for you, because you will want to make sure when you take this jump that things are happening on the device as you expect them to. Okay, so with that said, let's continue on. Again, because cuDF handles rolling windows, this ecosystem is just so great. Because cuDF handles rolling windows, Dask can handle rolling windows as well. So we can call rolling.mean.head on a data frame. Again, not terribly exciting, but like it's so cool because now it's happening on the GPU and it's happening really fast. We get all this nice feedback that we expect. So somebody was asking in the chat about larger than GPU memory workflows. How does that handle? And I believe we should have pointed them at Dask CUDA. I'll just bring that up really quickly. So those are in the docs. Also, I think just trying to demonstrate how you kind of navigate this ecosystem. So all of our docs are in docs.rapids.ai. Come to Dask CUDA. We have a nice spilling guide about how to do things and even some advanced things as well. Earlier, I believe yesterday, Mads, an engineer that works on the Rapids Dask team, gave a talk on advanced memory spilling. So you should check out that talk if you're interested in it. So again, because we set that device memory limit, we'll start spilling when we go over 4 gigabytes. So what we expect to see, this is going to take a little bit of time, but what we expect to see is, sorry, this is actually just persisting the data, so we won't really see anything, but we're seeing some memory option. What Dask is actually holding on to, which tasks were being processed, and this was just us constructing the data and then calling this memory usage. So this tells us that we have 5 gigabytes of data held in memory spread across 2 GPUs. There's also a nice, we also really wanted this feature. So there should be memory usage per partition, which is also quite nice in case you're wondering about how things, sometimes you care about skew and you want to make sure that partitions aren't empty or partitions aren't bigger than another. There's other ways of going about this, but this is a nice kind of sanity check that everything is equally distributed amongst our partitions. Okay, so now on to spilling. So shuffle is a rather intense operation. You shuffle, in this case, is not something that users typically call, but they'll call it within set index or within sort. You have to move all the data around and figure out how it needs to be reorganized. Or Dask kind of does this automatically. And now what we're seeing is a lot of these disk read, disk write. There's these red bars that are communicating between the GPUs. Again, that we're spilling here because we told the device to spill at more than 4 gigabytes. That comes up that comes up fairly frequently. The reason that it comes up is because 1, GPUs are resource constrained, like I said, and 2, because libraries will sometimes need to allocate some memory to do a particular operation. This also happens within pandas and within NumPy, where in a given operation, it will need to store temporary, it will need to do something that causes it to call CUDA malloc or malloc in the case of NumPy things. And those particular operations are things that Dask is not aware of. So you might, if you are at the edge of what your hardware can do, you might need to spill more frequently or a little bit earlier because these other algorithms need, or these other libraries need to be able to call in and get extra memory. I'm sure that people here have had Dask worker out of memory errors. Spilling is usually the answer that we recommend if you want your workflow to succeed. The easiest answer is just go get more memories. This is also where sometimes in my job, I will say, well, let's force all the hardware engineers to just go give us more memory. This is really annoying that we have to work so hard because we really want to saturate the device. And it's different than what other GPU computing looks like. When you're doing data analysis, you're really pushing the memory to the edge. Other kinds of GPU computing, deep learning, or drawing triangles, it's pushing on the computational aspects and the hyper-threading nature of GPUs. And data analysis pushes on both in ways that we are still exploring. Yeah, so we can also write custom functions in Dask. These things will also just automatically be compiled with Numba down to the GPU and distributed. So we can write nice lambdas, and those are just handled. All this stays GPU side. Again, the key, if you recall that first slide that I showed, where we were moving from Hadoop to Spark to GPU land, the reason that things stay performant is because we're not, or one of the reasons is GPUs are fast, but in addition to that, we're not moving back and forth. We're not doing costly transfers between device and host. That's the goal of all of these things. That's also where it's just really hard to do unless you are a CUDA expert. And also why libraries like Rapids exist. It's I mean, when I was a graduate student, I had to write some diffusion code. It was really hard to find the context where that was worth moving all the data to the GPU and running those computations. Now with Rapids, with tools like Dask, all of those things are handled for you. You shouldn't have to worry about those things. Sorry, I'll keep on moving along. So we have.
And Ben, just for your timekeeping, it's 10 minutes till the end of the session. So.
Oh shit! Sorry. I'm sorry, Nick. Okay. Well, so
no, you're fine. This is the core session notebook anyway, so it's really important that we spend the time here.
Sorry for cursing. I got nervous.
Oh, good. Just adding some flavor to it.
Okay.
That's good.
Yeah. The Dask delayed API is really nice. Nick could probably. Do you want to just speak over these set of this set here of like how you used this in the past, Nick?
Sure. So the example that Ben has up in front of him now is a demonstration of how we can use the Dask delayed API just like we would normally use it, except again keeping everything on the GPU. In this specific example, the task is to run linear regression on all sorts of different combinations of features. In this case, 1,225. So all you have to do is what you would exactly do on the CPU. You want to run 1,000 linear regressions, so you write that as a delayed function. You scatter your data to the GPU workers, and then you just append the futures into a list, and then you compute the list or persist the list, depending on what it is, all at once. And the results, in this case, each individual regression ran on the GPU, which is great because it's accelerated, and it spits out exactly what you'd expect for the Dask delayed API. It is the same interface.
Thanks, Nick.
Yeah.
Maybe we should get. Parquet handling is also here. It's magical. There's Parquet readers that are built into cuDF. Because those things exist in cuDF, we can leverage them inside of Dask. So not just efficient Parquet reading, but also ORC or CSV, JSON. There's a talk later on about how to make I/O even faster from Leo. I forget his last name, but I believe that's tomorrow. Is it worth, Nick, do you want to take over?
Sure. Sort of just to finish this notebook, the Parquet APIs can be a little confusing to folks not familiar with that format. So we go over it here, and there's lots of narrative in the notebooks because the thing about non-CSV formats, things like Parquet or ORC, is that they expose metadata and they let you do things that are highly efficient. And Dask is really great about that. And this part of the notebook just goes over how you can do things like choosing how to split on Parquet row groups and things like that.
Yeah, that's a good point. This line especially was kind of a big take home that took a lot of time to learn. Nick was the person that probably spent the most time here, or other people on his team, where you want to find how big should the data be? How big should partitions be to really saturate the device and not blow out of memory? This is where GPU data science looks a little bit different than traditional data science on the CPU, though still you can still tune how big chunks are. Yeah, this notebook is actually excellent, and I'm sorry that I ran over, but maybe, Nick, do you want to go over the end-to-end example? Should we end with that?
Yeah,
okay.
I will shift to share my screen.
Okay.
So we have 2 notebooks left in the next 6 minutes. What I will do is go through parts of both of them to make sure that we cover the right content. And I will go through this first one very quickly. We've already talked about how Rapids and Dask work nicely with a lot of different data types, traditional data. But we really want to drive home that it's not just about numeric data. It really is not just that. And so this notebook illustrates a small subset of the functionality that's available for complex NLP processing. And it just builds up 2 small examples iteratively that each read and process different data sets, one of which processes Twitter data, in this case, 300,000 tweets related to COVID back in April of last year. And it just illustrates how you can do things like tokenize the data with the .string accessor, .str, just like in pandas. We can tokenize the data. It's a really nice little function. And of course, we can choose how we tokenize with different things. But so that means to do things like get the word counts of the most common words, we can do that instantly with just tokenize value counts. But of course, these are not the words we probably care about. These are canonically considered stop words in the NLP world, words that don't really matter. We often want to ignore. So we can just ignore them. And so what we can do is, in this case, I'm just chaining functions. This is something you may not have seen, but you can chain functions together with parentheses, just like I did up here. So I'm just essentially doing a replace tokens before I tokenize. And I'm replacing the stop words with an empty string. And so now they're gone, which is great. But there's very clearly things going on with capitalization and case sensitivity. So we should probably convert everything to lowercase. So we do that, and now we see that, okay, well, there's a dash, there's a semicolon. Punctuation is probably important too. So we can also replace punctuation with the .replace API. We can replace all of these at once in the same operation. And okay, so now we've got new word counts, but the top word counts are co and HTTPS. These are web addresses. This is from Twitter. It makes sense that there's a lot of URLs in this data. So let's just add to the stop words, put in the co, HTTPS, and so on. And we can keep going and build this up. In this case, we saw that there's a bunch of new lines. So we can just add space normalization into our little pipeline. And by the end of this, we've got tokens that we think might be among the most common. But what if we want bigrams? We can do n-gram tokenization. cuDF lets us do all of these things. In this case, I'm going to go fast. I'm just walking through another example of doing trigrams. All of these things are parameterized to give you expressivity to fit your workload. But what's most exciting is that we can do the same code I just ran, like this exact code. I'm going to just copy paste it. And we can do it with Dask. In this case, I'm using 4 GPUs, and I'm doing a larger amount of the data. Using 4 of these GPUs, I'm sorry, I'm just going to get my little lab extension going. Using 4 GPUs, I can, I'm not sure why the task stream's not coming up on the side, but I can just have it up at the top here. Well, actually, I already have one running, so that's probably why. But regardless, in this case, we can do 5 million records. And actually, I will kill this just to make this run smoothly. It's worth taking an extra minute so y'all can see the full experience. So with 4 GPUs, we can process that whole pipeline on 5 million records essentially instantaneously, which is just really exciting. We get this wonderful API compatibility, and we can take that same code with our stop words and punctuation and just the same thing, and we just hit it with every identical API, and we get the full results using Dask with the same task stream and everything. This notebook goes into a broader example of using distributed TF-IDF and a very complex pipeline that's in code quite smooth, but essentially it does TF-IDF to process data across the workers, and then it does cosine similarity to allow you to do searching within a data set using Dask. It's something I encourage you to look into, but as we're about to finish time, I want to shift gears and instead quickly run through an end-to-end notebook. This notebook is doing several things, but for the most part, it's really representative of a canonical process of loading a bunch of data from a data source that is not clean. It's not ready, unfortunately. This data is just messy. And so in this case, there's 3 years worth of taxi trips from New York City. And so we have to read this data and clean it up. And so we can write a function to do that, which we do. And this function, I won't go into too much detail, but as you can kind of quickly see, it's just doing things like changing types and things like that. And so we process and clean this data, and then we clean some more data. And then we have to account for a messy pattern in the schema changing. And we do all this good stuff. And we have our data, and Dask just handles doing this on 16 GPUs. I think this is about 300 million records. And Dask just does it. We don't have to worry about distributing anything, even though it's on GPUs, not CPUs. So we can do exploratory analysis and look for weird trips with negative total time, or we can look for trips that are very short, but took $300 out of the pocket of someone who took the trip. That doesn't really make sense. Probably an outlier or a bad data point. And we can do that kind of work, and then we can keep filtering our data. And we can add features. We can do all the complex date time processing. We can do division of longitudes and latitudes. We can do all these even more complex things, like doing distance functions from another Rapids library called cuSpatial. This is the Haversine distance. And we can do all of these things, and Dask just kind of just executes it for us, just like you'd expect. It's very boring, as Ben said. This is just smoothly executing, and it's done. This was very fast because it's on 16 GPUs, but it processed hundreds of millions of records with complex geospatial processing and date time handling in 3 to 5 seconds. And the work that we've done with the community has led to a native GPU XGBoost integration with Rapids. XGBoost is a project maintained by DMLC. It's a fantastic project that we work closely with. And there's a native integration with Rapids and the Rapids memory and Dask, which has already been, the community's been leading for a long time, which is great. And so we can just, with one line of code, we can do xgboost.dask.train and just pass GPU hist. And this is identical to what you would do on the CPU. You could be doing this on any number of CPU nodes in the cloud or on premises. But here we're doing it on 16 GPUs, and it's no different. And you can see that it took about 20 seconds. And that's hundreds of millions of records being processed by XGBoost in 20 seconds. It's really exciting, and we get all the same wonderful attributes like feature importance that we expect. We can, of course, predict with our model, and we can do all of this entirely on the GPU, which you can sort of see in this panel on the right where we're doing predictions. You can see that we're doing it block by block. These predictions are parallelized. And then we can calculate our error, as we might want to do. We can save our model. Again, this is a Dask GPU XGBoost model. We can use joblib to just serialize it and put it on disk. And we can just load it again, and we can keep predicting. And so this ecosystem is incredibly exciting while simultaneously being so boring, which is really the goal of any product and project that someone wants to use. It's just, you don't have to think about it. And that's really a testament to the Dask community and to the sort of broader PyData community we've been working with. So that's 10 minutes of 2 of these notebooks. I encourage folks to take a look at them after this. I know we're a little bit over, so apologies for that.
Cool. Thank you so much, Ben and Nick. Yeah, and thanks everyone for staying over a little bit. I know that there's a keynote going on right now, so if you'd like to drop and join that, feel free to. Just a few things. That tutorial channel that I shared in the chat, that does have links to the slides and the notebooks. So I know we kind of rushed through the last 2. You can kind of get the full effect of them from the notebooks and that workspace rather channel. So thank you so much for joining. Thanks, Nick and Ben, for giving some great content, and hopefully we'll be talking to you over the Slack channel. Thanks, everyone.